Hi everyone, I am Ivan Sanchez and I show us how cesium-tin allied perovskite nanocrystals were synthesized by hot injection method in our laboratories. Basically, in a 3-neck round bottom flask, we prepare a precursor solution dissolving tin hexanoate and tin oxalate in 1 octadecene. Oleamine and oleic acid were used as a capping ligands for this nanocrystal synthesis. Because of tin 2 cations can oxidize to tin 4 plus cations under oxygen and moisture, precursor solution was prepared inside a glove box. Reaction flask was taken from the glove box and connected to the Schlenk line, where we carry out the chemical synthesis of perovskite nanocrystals. Reaction mixture was firstly heated for 1 hour in vacuum at 120 Celsius degrees until to dissolve tin salts and obtain a transparent solution. Finally, 1 milliliter of 0.4 millimolar solution of cesium olate preheated at 120 Celsius degrees was injected to the reaction system. Metathesis reaction between tin allied and cesium olate give rise to the formation of cesium-tin allied perovskite nanocrystals, observed as a color change in the precursor solution to red in the case of cesium-tin bromide perovskites and red-brownish from cesium-tin iodide nanocrystals. When these nanocrystals were irradiated with laser excitation, we do not observe visible color emission because cesium-tin allied perovskite nanocrystals exhibits infrared light emission. After 25 seconds, the resulting crude solution was cooled down to room temperature in an ice bath to stop the nanocrystals' growth. Finally, reaction vessel was put inside the glove box for purification and storage for future uses.
Inorganic selective transport layers combine interesting optical and electrical properties depending on their crystal size and shape that can be tuned through different synthetic techniques. The majority of them can be prepared through solid-state chemistry by simply mixing powder of reactants and calcining them to give the desired products. The main drawback of this approach is that the resulting materials are difficult to disperse in a solvent. The materials must fulfill several requirements to achieve a suitable electron and hole transport layers for DropIt project. These are processed from solution to be compatible with inkjet printing, good electrical conducting properties, high transparency in the visible, and baked temperatures below 300 Celsius degrees to be compatible with flexible substrates. Therefore, our approach to obtain thin films of selective transport layers is based on the in-situ synthesis of the metal oxide on a substrate after coating or printing a precursor solution called ink of a given metal salt. The main advantage is that this method is compatible with many standard coating and printing techniques with good compositional control. This is our new high peak power laser. The main unit is a pulsed 400 picoseconds optical fiber laser at 1064 nanometers, followed by a tunable pulse compression unit from 400 femtoseconds to 20 picoseconds. Finally, the laser incorporates nonlinear crystals for doubling to 532 nanometers and tripling to 355 nanometers. Here, we show the setup where we characterize wave-guided light emitted by the active material, in our case, the lead-free perovskite film, deposited by inkjet printing on a transparent flexible substrate as we can see in the floating video. When laser excitation is high enough, amplified spontaneous emission is outcoupled from the waveguide and analyzed with the spectroscopical setup. Now we see an open-access microcavity system for studying lasing of semiconductors. The microcavity consists of a planar distributed black reflector, DBR, where a perovskite thin film can be deposited, and a carved DBR patterned on an optical fiber. This system combines several advantages: realization of a small mode volume, a certain wavelength tunability, and easy integration with different types of perovskite emitters. This is the setup we use for photoluminescence of lead-free perovskites under steady state and transient condition, using an appropriate excitation lasers as a function of temperature. This gives us information to understand the exciton carrier dynamics of the material. Here, the optical setup is similar to the previous one, steady state and transient studies, but using confocal conditions for photoluminescence excitation and detection in such a way that we can investigate small nanocrystals or two-dimensional nanosheets of perovskite, for instance. Furthermore, the cryostat used here is vibration-free, which is suitable for the study of nanoscale materials.